Hi friends and my dear students, I welcome you all for yet another interesting session today, and that is crystal lattice and unit cells. Okay. In fact, friends, this is the most important topic of the entire chapter. So please pay more attention throughout the video, because if you get a grip on this topic, you can easily understand the rest of the chapter. Fine? But before I get into the topic, let us take a look at this beautiful tile floor and this wall made of bricks. But you may be wondering, why am I showing these, isn't it? Yes. Could you figure out something common between these two? Yes. If you carefully observe both these, in fact, you can find a regular and a repetitive arrangement of points in a definite pattern in two-dimensional or three-dimensional space, right? Yes, such a regular and a repetitive arrangement of points in space is actually called as space lattice. Okay, friends, let me now explain the concept of space lattice in a much more elaborate manner by considering the example of tiled floor. Yes, nowadays there are so many different types of tiles available with different shapes and designs, isn't it? You just have to pick up one such tile with a particular shape and design of your choice. And when such tiles are placed one next to each other in the entire floor, you get such a beautiful tiled floor, isn't it? So we get a repeated pattern here, isn't it? Okay, now let's say we mark a point at the center of each and every tile, and for a while we'll ignore all the tiles, but just carefully look at only the points now. Can you see this set of points is actually showing a regular pattern in the two-dimensional space? Yes, friends, this is actually called as space lattice. Okay, now let us extend the same concept to our crystalline solids. Okay, we know that a crystalline solid is made up of a large number of constituent particles, and these particles are arranged in a regular manner with a definite pattern, isn't it? Now, let us replace these particles by certain representative points. Then we get a crystal lattice. Okay. Therefore, such a regular arrangement of particles of a crystal in the three-dimensional space is actually called as crystal lattice. Okay. So, having known a crystal lattice, let us now proceed to discuss its characteristic features. For that, please take a look at the crystal lattice. Can you see there are a large number of points here in all the three dimensions? Yes, here each and every point of the crystal lattice is actually called as lattice point or lattice site. Okay, and every lattice point represents a constituent particle. And we already know that a constituent particle can be either an ion or an atom or different types of molecules, right? And can you see, friends, all these points are joined by lines to represent the geometry of the crystal lattice. So, friends, until now we have seen what is a crystal lattice and its various characteristic features, isn't it? Now, let us learn what is meant by an unit cell. Okay. For that, please take a close look at the crystal lattice once again. Can you see a small group of lattice points is actually repeating itself over and again in different directions to form the entire crystal lattice? Yes, such a small group of lattice points in the crystal lattice is actually called a unit cell. Okay, now we can define unit cell in this way. It is the smallest three-dimensional portion of the crystal lattice, which when repeated over and again in different directions forms the entire crystal lattice. To understand this, let us consider the example of the wall made of bricks. Take a look at this wall. Can you see it is made up of so many bricks? Yes. Here, the brick can be compared to a unit cell, whereas the entire wall can be compared to what? Definitely the crystal lattice, isn't it? Okay, friends, observe this unit cell carefully now. Around this particular point, can you see three edges? Let us call these edges as A, B and C along X, Y and Z axis. Okay, but please make a note, friends. These edges may or may not be mutually perpendicular. Okay, now in every face, can you see an angle being formed between two edges? In fact, such an angle is called as face angle. Now let us look at the different face angles in this unit cell. Okay, watch this unit cell once again carefully. Between the edges B and C, an angle is formed. Can you see that? Let's call it as alpha. Similarly, between the edges C and A, an angle is formed and that is called beta. And between the edges A and B, one more angle is formed and that is called gamma. Therefore, friends, overall a unit cell is characterized by 6 parameters. That is 3 edges, or we can say edge lengths, that is A, B and C, and 3 face angles, that is alpha, beta and gamma. Okay, friends, now let us learn about different types of unit cells. Fine. In fact, based on the position occupied by the constituent particles, unit cells can be broadly classified into 2 categories. They are primitive unit cell and centered unit cell. Now, firstly, take a look at primitive unit cell. Here, the constituent particles occupy only the corner positions, isn't it? This is also called as simple unit cell, okay? Because here the constituent particles occupy only the corners of that unit cell, okay? Now let us take up centered unit cells. Here the constituent particles not only occupy the corner positions but also they occupy some other different positions. Therefore, friends, based on the position occupied by the constituent particles at different places, centered unit cells are further classified into 3 types. They are body-centered unit cell, face-centered unit cell and end-centered unit cell. Okay. Now, take a look at this body-centered unit cell. Here, the constituent particles are occupying the corner positions of the unit cell. But friends, can you see there's one more constant particle which is present exclusively within the body of the unit cell? That means this constant particle is occupying the center of the body of the unit cell. Okay. Now, take a look at this face-centered unit cell. Here also the constant particles are present at the corner positions. But as you can see here, there are 6 faces, isn't it? And there is one constant particle occupying the center of each and every face, right? Now, take a look at this end-centered unit cell. Here also, the constant particles are present at the corner positions. But my dear friends, we know that there are 6 faces, isn't it? So, if you consider these 2 faces, that is the top and the bottom face, they are opposite to each other. And there are 2 constant particles now present at the center of these 2 opposite faces. Therefore, in an end-centered unit cell, you will have the constant particles both at the corner positions as well as at the centers of any 2 opposite faces. Okay, friends. So far, we have seen 7 crystal systems and 4 different types of unit cells. So, you may be wondering, actually in nature, how many types of lattices are possible? This was first discovered by a French mathematician by name Bravais. He discovered 14 types of lattices and these are called Bravais lattices as a mark of respect for the discoverer, that is Bravais. But still, you may be getting a doubt. Why only 14 types, isn't it? In fact, we have seen 7 crystal systems and 4 different types of unit cells. Still, how only 14, isn't it? This is because actually each and every crystal system is found to exist in a specific number of unit cells of different types. Okay, therefore we have only 14 types, right? Shall we see what are those 14 types of lattices? Yes, friends, just now we saw different types of unit cells, that is primitive unit cell and centered unit cell. Also, we learned that a unit cell is characterized by 6 parameters, that is 3 edge lengths and 3 face angles, isn't it? A, B, C, and alpha, beta, and gamma. Once again, unit cells are of 7 types based on the variations in edge lengths, that is ABC, and face angles, that is alpha, beta, and gamma. And these 7 types of unit cells are in fact called as crystal systems. Now, this is very, very important because innumerable questions have been asked on this particular concept in this chapter, both in board exams as well as competitive exams. So, you have to remember all these 7 crystal systems. So, to make it quite easy to remember, I have tried one trick for you guys. Are you ready? Shall we look at the trick now? Yeah. The trick goes like this. Cub and tiger got an orange, gave it to monkey, asked it to try to put it in a Tetra Pak, but it wanted a Hexa Pak. Now, you'll be wondering why we have highlighted these letters, isn't it? Yeah, just catch these letters. Let me highlight once again. Cub and tiger. So, these letters indicate the names of the corresponding crystal systems. Look here. If you remember cub, this will be the starting letters for cubic, right? And if you remember this T or tiger, tie at least, from there you'll get tri, okay? Trigonal. Got it? Orange, or. From or you can remember orthorhombic. Look here, orthorhombic. From monkey, that is M-O-N, you can remember monoclinic. M-O-N again. From tri, you can remember triclinic. From Tetra Pak, you can remember tetragonal. And from Hexa Pak, what did you guess? You can remember what? Hexagonal. Okay. First of all, I have given you this trick so that you can remember the 7 crystal systems in a particular order. Okay. Yeah. Now let us look at the 7 crystal systems and see how we can actually group them based on certain logical basis. I'll tell you what is that. So I have grouped them into 3 sets like this. Cubic and trigonal, remember in the same order. It's very easy based on the trick, right? That is cub and tiger, orange, monkey, tri, isn't it? This is second set in the same order. Tetragonal and hexagonal. Third set in the same order. In the books, probably the order might be different. So don't worry about that. Order doesn't matter. Okay, you need to remember the, edge lengths and face angles of each and every crystal system. Okay. Now, if you look at this tabular column, you may be getting scared, isn't it? Please don't get afraid because I'm going to make it very, very simple. Axial distances I've mentioned here and axial angles, they are synonyms for, edge lengths and face angles. Don't you worry about that. And we have also given the corresponding examples there. 1 or 2 examples you have to remember. Okay, now I'm going to apply the trick so that you will remember all these variations in edge lengths and face angles very easily. Shall we do now? Now I told you I have clubbed these 2. That is the first set, cubic and trigonal. The second set is orthorhombic, monoclinic and triclinic. And the last set is tetragonal and hexagonal, isn't it? Why have I done like this? Yeah. Look, these 2 have the relationship between all the 3 edge lengths common. What am I trying to say? Yeah. Look here, A equal to B equal to C. Here also A equal to B equal to C. What is the meaning? That means all 3 edge lengths are equal to each other. This is very important. They have the same edge lengths. Clear? In other words, the edge lengths are same. Okay, fine. Now, the first one in every set. In this set, this is the first relation between the face angles, isn't it? Similarly, here the first one is orthorhombic. Let's underline that. This is the first one in this, first one here and first one here. If you watch carefully, look here, for orthorhombic also, it's the same thing as this. Alpha equal to beta equal to gamma equal to 90 degrees. Similarly, the first in this third set is tetragonal. And once again, you can see alpha equal to beta equal to gamma equal to 90 degrees. So, in that way also, you can remember this order. Okay. And it will be easy for you to remember these face angles. Now, let's go one by one. So, cubic we have seen A equal to B equal to C, and all the 3 face angles are equal to each other, and also all are equal to 90 degrees. That is the meaning And the examples are there right in front of you. I don't have to read it for you, I hope. Okay. Now, trigonal, or it's also called rhombohedral. Any one you remember. Once again, I told this is common, so I don't have to say that. But here, just remember this. That is, alpha equal to beta equal to gamma, but not equal to 90. Okay. That means all these three are equal to each other, but none of them are equal to 90 degrees. That's the meaning. Just now I said for orthorhombic, it's easy to remember. This is the first in the second set. Look, this will repeat. Okay, so we know the phase angles now. And if you watch carefully in the second set, that is among orthorhombic, monoclinic and triclinic, look here, this is the common thing. A not equal to B, not equal to C. Same thing throughout in this set. In that way, I have actually clubbed. Okay, that means all the three edge lengths are not equal to each other. Right, and this first one you know. Now, in this monoclinic, mono means we can think it as 1, isn't it? So that 1 we will take it as beta, we'll remove the beta out, but the rest 2 are alpha and gamma. So far only 90 degrees, therefore alpha equal to gamma equal to 90. That we also can remember. But that mono, that is 1, that is beta, we'll remove, and that beta is not equal to 90 degrees. Okay. Triclinic, tri means we can think it as 3. So all 3 are not equal to 90 degrees and they are not equal to each other also. Alpha not equal to beta, not equal to gamma, not equal to 90 degrees. Are you clear? Tetragonal, right? And hexagonal. That's a third set. So how did we club them? Look, this is the common thing once again. A and B are equal, but B is not equal to C. See, A equal to B not equal to C. Is this clear? Okay. Again, the first one we know. You have to remember that. I told you that it's common, right? It's repeating in fact. And in hexagonal, you can, now in this case, you remove beta. In this case, you remove alpha. That's it. And these two, as usual, 90. That is alpha equal to beta equal to 90 degrees. But gamma is 120. How to remember 120 if you ask? Maybe you can take hexa as 6. And this is 2 things out. Fix 2s are 12. Put 1 0. So 120. That way also you can remember, right? So all these are the examples. How much ever I try to explain, either using a trick or with so many attractive words, still I don't think it is that catchy, isn't it? So it will become very, very clear to you, provided you look at all the beautiful images and try to relate these theoretical concepts, okay? Then only you'll understand better. So please retain a smile on your face, okay? So let's look at the images now. The 7 crystal systems. Firstly, cubic. Now, applying the trick, right? Cub, cubic. So, what did I say? This is the first in the order, right? Therefore, here A equal to B equal to C. That's the first thing you should remember. And alpha equal to beta equal to gamma equal to 90. Remember? Apply the trick, please. Look at this. Look at the image. This is cubic crystal system. Did you get that? Yeah. And of course, 1 or 2 examples once again, so that you can relate the example and its values of edge lengths and face angles along with the image, so that you'll get a complete picture. Hope it's helping you. Shall we move on then? Yes. The next one now. The next one is what? What did I say? Cub and tiger. That means trigonal, right? Also called rhombohedral. Yeah. What did we say again here? A equal to B equal to C, that is common, right? A equal to B equal to C is common, but look, what did we say? Alpha equal to beta equal to gamma, not equal to 90 degrees, okay? That is the structure. Let's go ahead now. Third one. What's the third one? Cub and tiger got an orange. Or means orthorhombic. Look, what did we say? Yeah, here, look, all these are not equal, and this again, alpha equal to beta equal to gamma equal to 90 degrees, and that is the structure, okay? And these are the examples: rhombic sulfur, potassium nitrate, barium sulfate, etc. Shall we go to the next one? Yeah. Fourth, monkey, monoclinic. Yeah, once again here, A not equal to B not equal to C. That is same, no? But I told you to remember, mono for 1, 1 means remove beta. Maybe you can remember 1 like this, beta, right? It's a very vague trick. So 1 mono for 1 and 1 you can remember like this and put beta. Okay, that we also can remember. So alpha equal to gamma equal to 90, beta not equal to 90 degrees. We have already seen that. So let's move ahead now. Fifth one, after monkey, they asked you to try, isn't it? So try for triclinic. Once again, A not equal to B not equal to C, that is common thing. And here tri means I said 3, remember? Therefore, alpha not equal to beta not equal to gamma not equal to 90 degrees. And that is the structure, please. Sixth, after trying, yeah, it asked you to put in a tetragonal, that is tetra pack. Tetragonal, tetra pack, right? Yeah, here the common thing, A equal to B but B not equal to C, and that's the first in the third set. Therefore, that is common again. Alpha equal to beta equal to gamma equal to 90 degrees. Y10, SNO2, etc. The last one is, yes, hexa pack it wanted, means hexagonal. Once again, A equal to B not equal to C, that is common. And I told you hexa means 6, isn't it? So 6, and you have taken these 2. So 6 2s are just a very, very vague trick. 12 and put 0 here because there is a 0, right? So that 0 you can think, and therefore you get 120. And this time you are taking out gamma. So alpha equal to beta equal to 90 degree, but gamma equal to 120 degree. The examples are graphite, ZNO, etc. Okay. Hope the trick was useful. Please apply this trick and try to remember the 7 crystal systems, because you're sure to get at least one question either in board exams or competitive exams. Okay, guys? Okay, shall we look at the 14 types of Bravais lattices? Yes. Firstly, we'll take up the cubic crystal system. That is the first in the series of the 7 crystal systems we know. So, as I told you, under this type, only 3 types of unit cells are possible. What are they? Yes. Simple unit cell, face-centered cubic unit cell. Okay, in short, we can say FCC, face-centered cubic. Okay. The third one is body-centered cubic, in short, BCC. Shall I show you the images now? Yes. So, under cubic crystal system, the first one is simple unit cell, and this is the structure. Why it is simple? We know because the particles are present only at the 8 corners, right? Very good. What about FCC? Here you have both, yes, particles at the corner positions, right? And also one particle at the center of each face, and there are 6 faces. Therefore, it is FCC. We know this. Okay. The next one is BCC. So, in BCC, you know, the particles will be at the corners. Along with that, there is one particle in the center of the body of the unit cell. That is at the body center. Good. So, shall we move on to the next crystal system now? Yeah. The second one is Trigonal crystal system. Under this, you have only one type of unit cell possible, and that is the simple type. So, this is the structure. Okay. Good. The third one is Orthorhombic. Under Orthorhombic crystal system, 4 types of unit cells are possible. Okay. And all the 4 are here. Simple, face-centered, body-centered, end-centered. Okay. Here we cannot say FCC because FCC is face-centered cubic. But this is face-centered under orthorhombic. Okay. So, shall we have a look at it now one by one? Yeah. To begin with, the simple type under orthorhombic crystal system is this. Okay. Good. The second is face-centered under orthorhombic. Once again, you have the particles both at the corner positions as well as at the centers of the faces. Body-centered, once again, yeah. And end-centered, as we know, you have particles at the corners, and the 2 opposite faces considered here are, once again, the top face. This is the top face, and this is the bottom face. Okay. So, you have a particle here and here at the center of these 2 opposite faces. Therefore, it's end-centered, but coming under the type orthorhombic crystal system, right? Shall we move on to the next type now? After orthorhombic, monoclinic crystal system. Under this, we have 2 types of unit cells possible, and they are simple and end-centered once again. And take a look at the images. Simple under monoclinic and end-centered under monoclinic once again. What's the next one? Triclinic crystal system, right? Under this, once again, only one type possible, that is a simple one. So, this is the structure. Let's move on. That is tetragonal crystal system. Under this, 2 unit cells are possible and they are simple and body centered here. And the images are here for you. This is a simple type under tetragonal and this body centered under tetragonal once again. The last one is hexagonal crystal system. Under this again only one type of unit cell is possible and that is simple. Okay, and the structure is here. Please mind you, my dear friends, this highlighted portion, okay, represents the unit cell. Fine? Good. So, now this tabular column will give you the overall picture wherein we have shown you the crystal systems, all the 7, as per the trick that I have taught you, isn't it, earlier? And therefore, we have cubic and trigonal as one set, orthorhombic, monkey, that is monoclinic, and triclinic, tetragonal and hexagonal. Just now we saw under cubic 3, isn't it? Simple FCC, BCC. Under trigonal we saw only one type, that was simple. Under orthorhombic we saw all the 4, as you can read it here. And monoclinic only 2, that is simple and end-centered. Triclinic 1, only simple type we saw. Tetragonal had 2 types, that is simple and body-centered. We saw that just now. Hexagonal has only one type and that is a simple one. So just add it up. 4 plus 4, 8 plus 2, 10. 10 plus 4, 14 types. That's what I told you. 14 types of lattices as discovered by Bravais. Okay. We have come to the end of this session. Hope it was very useful and you have enjoyed thoroughly, I think. So until we catch up in the next video with yet another interesting topic, please take care. Bye-bye.